My question is why the property of this solution is being like this. So soap can dissolve into water. Fats cannot dissolve into water. But when you mix fat and the water, then you drop some soap inside, you can redissolve everything as a homogeneous solution. How can we explain this kind of behavior? Okay, so if you haven't done it yet, do it right now. Okay, but if you finish, then continue the video. I will give you the correct answer for this question. First of all, I will talk about soap and water first. For the soap, as you can see, the molecular structure composed of two sides. We have long chain hydrocarbon on the right hand, which is insoluble into water because you have so strong London force that can attach with each other. So normally the soap bar, as you normally see, it's come by the London force packed up together, and again on the left hand side you have sodium ion and carboxylate ion. This is very high polar, so you have electrostatic charge, right? So you have ionic kind of ionic bonds and London force for the soap bar. But when you dissolve into water, as I mentioned earlier in the content about the London force, that the long chain hydrocarbon here cannot interact well with the water. So they tend to have the interaction with themselves. Okay. In the first case, if you dissolve this thing into water, right, sodium ion and carboxylate ion has weak interaction against each other. So they separated by the water molecules. So sodium ion is now surrounded by the soap molecule. And also for the carboxylate ion, you have also soap molecules, water molecules come around, okay, and dissolve them. So you have this kind of interaction, ion dipole interaction. So with very low concentration of soap, you may see that the solution is quite clear. So apparently, if you have a jar of water and then you put the soap bar, right, just dip in and take out really quickly, very quickly. So what you can see is the solution is clear. But if you, instead of dipping down, right, you just swirl it into the water for a little moment. So what you can see is that you can have a kind of cloudy solution, or cloudy colloid to be precise. Because if you have many molecules of soap, right, they're starting to have interaction with each other because if you, with the higher population, the side chain with its non-polar can then comes together using London force to pack themselves up together. We can call it as hydrophobic interaction because they tend to stay together rather than stay with the water, right? So what we can have is the hydrophobic interaction. So instead of this kind of thing, I depict it like this. We have negative charge of the carboxylate, a long chain hydrocarbon like this. So if we have many molecules of the soap, what we can have is the long chain tends to stay together by the hydrophobic interaction. Anyway, you have negative charge. And again, negative charge tends to repel each other electrostatically, right, by Coulombic force. So same charge, stay away from each other. So as you can draw, this is a structure resulted from such kind of interaction, right? So as you know, I normally call this as interaction. I didn't call the intermolecular attractive force, right? We called it interaction because we have both attraction and repulsion. So as you can see from the picture here, negative charge repel each other by electrostatic repulsive force, right? So they want to stay away from each other. But the long chain here they have to stay together because they have less interaction with water. They bind together stronger than that. So you have this kind of thing. So when you have higher concentration of soap into water, you can have the cloudy colloid. And this is the structure of the cloudy colloid, which is called micelles. So in the micelles, as you can see from the picture, that inside here is hydrophobic interaction, or actually it's the London force. And we have electrostatic repulsion. Among the negative charge of the carboxylate. And then you also have the ion dipole interaction around here because of the charge of the soap, of the carboxylate, and the dipole moment of the water. So as you can see, I'm trying to draw hydrogen towards your soap molecule, right? Because of the positive pole of your hydrogen atom in the water can have interactions with your soap negative charge. So here is the ion dipole interaction. But if you look at the fat, it's very non-polar and very huge. So London force among the fat molecules are very strong. Hydrogen bonds of the water are very strong as well. So to dissolve the fat molecules in water is impossible. This is maybe due to the induced dipole interaction between water and fat is not enough to destroy the London force of fat and also to destroy the hydrogen bond of the water. So two components cannot blend in together, right? But if you have fat and soap together, fat molecules is non-polar. That means you can have London force with the long chain side of the soap very easy. So fat molecules can come here in the center. So we have fat here inside. So the fat molecules and the soap can have such a strong interaction of London force. Again, it's hydrophobic. So we can have hydrophobic interaction among the soap molecules together or between soap and the fat molecules. Okay? So without the soap, we cannot dissolve the fat into water because you don't have any polarity, the polar part of the molecule inside. Actually, the ester is slightly polar, but it's not enough, right? Because you have very high, huge area of non-polar part here in the molecules. Unlike the soap, you have smaller area of non-polar, and you have very high charge density over here, which can react with water very easy. So you need the soap in order to dissolve the fat into water, and this is all the possible interaction observed in the solution system. So actually it's not the solution, it's the colloid, because the solute is not small, okay? It's quite huge. As you can see, we can have the intermolecular assembly, right? The soap molecule assembled themselves together in a spherical. Actually, it's not flat, it's sphere. Okay, so this is called molecular assembly. So as I said, that the intermolecular interaction does not only describe the physical properties like melting point, boiling point, and the dissolution of things, but it can also describe the molecular assembly like this in the system as well. Okay, and this is all about the dissolution of soap into water.